السلام عليكم. بسم الله الرحمن الرحيم. رب اشرح لي صدري ويسر لي امري واحلل عقدة من لساني يفقهوا قولي. So today we are going to continue with chapter 5. In chapter 5 we have been talking about distributed forces and how these distributed forces are acting on in real time, because in past chapters we were talking about different techniques of equilibrium forces, how to solve a statically determined system, and then from there we went from a statically determined system, how to solve those systems in 2 dimensionals and 3 dimensionals, and we comprehended so far the general understanding of Newton's second law, that F is equal to ma, the inertial property when it is at equilibrium. And that's why when we talk about space trusses in the last chapter, we were talking about 3-dimensional trusses. During these all in the entire chapter, the entire book so far, you have been talking about equilibrium, sum of forces equal to 0 in x, y, z axis, and sum of moment equal to 0 in x, y, x axis. Then we are talking about now a very important part of these forces. What exactly is a force? How they are acting on a body. So the chapter 5 is talking about distribution of forces. From there we came to know there are certain things. What is a center of mass, which you have if you have taken the previous lecture, you would have realized now it is an important part. The center of mass is based on geometric property, and it will give you the center position of mass, not acting under any kind of force field. One of the basic force field is gravitational force field. Now, gravitational force field, when it is introduced and you place your mass inside a gravitational force field, you develop a weight. So now you have a center of weight, and that center of weight calls mg. Since g is uniform, so your center of weight is also introduced. Now you have to understand, for uniform bodies like a rectangle, like square or cube or a spheres or any other geometrically symmetric bodies, the center of mass and center of gravity, they coincide. So it solves most of the problem. So for this part of the chapter, we are going to say the center of mass and center of gravity, they are at the same point. Then we came to determine different conditions such as lines, areas, and volumes. In reality, we don't have lines, we have ropes, or we have pipes, we have tubes. Areas can be thin surfaces. They still have thicknesses, but the thicknesses can be considered as negligible compared to their mass distributions. And then we have volumes. And then how can we determine the centroids of lines, centroids of areas, and volumes? We studied in past chapters. Then we talk about composite bodies. Composite bodies means you have non-homogeneous distribution of masses over a line, over an area, or over a volume. So one of the techniques we discussed in the past lecture was the theorem of Pappus. The theorem of Pappus is a very simple theorem. It just talks about a thin cross-sectional area of a straight line, and it is rotated about a certain axis of rotation, that it can be about any axis of rotation, to form a surface, a circular, or you can say cylindrical surfaces. And with that surface you can generate the centroid of that surface. Now you have to remember, the centroid can be inside an object or can be outside an object. Centroid is a point where the object will concentrate its or put its resultant force. Then we talk about Pappus is 2-part. If you remember, there is to define the surface through a thin line, and to define the surface through a certain cross-sectional area to generate a volume. So thus far we talked about different surfaces. We talked about centroid, the lines, the composite masses. But the question is, how can we define a beam on a truss and the forces on that beam? These are important. So in this topic, we are going to talk about beams. Now, this is interesting. Okay, there we go. We got it. Beams. Now, yeah, this is a very important part. The beams are structural members that offers resistance to bending due to applied loads. So, right on top. That is true. If you look around you, you have beams all around you, and their intended purpose is no matter how much load you apply on them, they are not supposed to bend. Now, we say if there is extensive loading and beam starts to bend, this is considered a failure of your system, or failure you have designed, and it's bending. This means you are putting load, too much load, and the beam cannot handle it. The beam is not providing enough resultant forces or reaction forces so it can generate an equilibrium. So a basic definition would be to generate an equilibrium system, not a non-equilibrium system, because the defined definition should be of our desired output. Now, the first line here, the beams are structural members which offer resistance to bending due to applied load. It is correct. It's not only just bending, it could be anything. It could be torsional, rotational, but they are different types of forces. What we are focused on beams is the external forces. How does the environment react to our beams? In general, you can say what is a beam? We have defined definition of beam, but beam does not necessarily mean it has to be a straight square rod. It could be anything. This beam could be a simple cylinder, could be an I beam, could be an L beam, could be a T rod or a simple hexagonal rod. Based on your design or your structural frame, it can also be a simple triangular surface. Now, these beams, if you look at them, they have to be connected externally to certain structure, or to support, or to certain joints. Now, the beam are divided into two parts: statically determined beams and statically indeterminate beams. So what are the two? What's the difference between the two beams? Now, statically determined beams are simple beams when you develop their equations, sum of forces along x, y, or z axis equal to 0, and sum of moments along about x, y, and z axis is equal to 0. Your number of unknowns and number of equations will be the same. But a statically undetermined beam usually have more you can say stabilizing structures or stabilizing supports, or less stabilizing support. This means you will always have large number of unknowns and less equations. In order to understand the two types, let us look at the figure on the left. If you look at this three beams in a column, there's a simple beam, a cantilever beam, and a combination beam. And you should see, look at the bottom, it says statically determinate beams, and you can see it's very easy. Let me show you how. Look at the reactions. You have to understand the reactions. It's pin joint right here, and pin joint is going to provide equal and opposite reaction along one axis. And then you have a roller joint on the other side, and up we have the second reaction. Now, if you remember, if we develop a legend of this particular setup, we are going to find out that our forces are acting along y-axis, and we would have a straight x-axis passing through the beam right here. So rather than introducing y-axis right here, we can do is we can make our life simpler by passing the origin as this joint at the origin, and we got a coordinate system. And if you look at this thing, assuming the pin joint is considered as a joint and the roller joint is a B joint, what we can have is a sum of forces along y-axis equal to 0, that is one equation, and assuming the sum of moments about pin joint is equal to 0, then we have a second equation. So the two unknowns were the first reaction at pin joint and the second reaction at roller joint. So two unknowns and two equations. So our structure is statically determined. Same for second part, the cantilever beam. And if you look at the cantilever beam, it's the same thing. At this joint where it's connected to the wall, it will have only one moment, counter moment to this force acting downward, and a one reaction force at the center of this line to equal and opposite to this force. You will have two equations and two unknowns. Again, it is a statically determined beam. The two equations are sum of forces along y-axis equal to 0 and sum of moment about where it's connected, generated by reaction moment of the cantilever, to the force times the moment arm of the, or the length L of the cantilever. This means L times this force applied externally will generate equal and opposite moment. So we got two equations and two unknowns. This structure is also statically determined. Then we have a combination system. Again, it will have equal amount of forces up and up, and we can find these two reaction forces, the value of these two reaction forces, by number one, sum of forces upward equal and opposite to sum of forces acting downward. They should be equal and opposite, so they should be 0. Then we can say moment about pin joint should be 0. Yes, it is. As a result, you will get a second equation. This will provide you two unknowns and two equations. Now, if you look at the statically indeterminate system, this is important. First thing is a continuous type of beam. So the problem is it's not that the beam is not stable. The beam would seem stable, and you can see it is very stable compared to our simple beam, and you have an additional loading right in the center. But the problem is you don't know how the forces are distributed, how the forces and which part of the beam is taking maximum loading. Is it the center roller, or is it the far roller to the far right, or it is the pin joint? Your equations will be only one equation. If you remember it correctly, you can generate only two equations. Sorry, not one equation, two equations. Number one, let's draw our unknown variables. So number one reaction is at the pin joint. The second reaction is this roller joint in the center. The third reaction will be the roller joint on the far right. Now, sum of forces acting upward equal and opposite sum of forces acting downward. You balance them out, you will get the answer that has to be 0. That's the beauty of statics. You know the answer, and it's always 0. And then you don't talk about sum of moment about pin joint or any of the roller joints, and then you're going to talk about the reaction. They have to be 0. The problem again, realize you have three unknowns and two equations. You will not have a third equation. As a result, this is indeterminate solution. It may be overdefined. It can also be underdefined. Underdefined forces are problematic also. And let's look at the second, that is end supported cantilever. Same thing, you have two forces at the support joint, that is a reaction force acting upward and the counter moment generated by the force. Let me show you again. Same thing, a force and a counter moment at this point, and just a reaction. So you got three unknowns, and again you're going to develop two equations. Sum of forces acting upward should be equal and opposite to sum of forces acting downwards, and generated by the moment of that force about the fixed end it will create that fixed end is also going to create an equal and opposite counter moment. So you got 3 unknowns and 2 equations, undetermined. And then now you have 4 unknowns at the fixed point. This is a fixed structure. As you can see, you have a reaction on both the ends, either ends, and you have a counter moment generated by both ends. So you got 4 unknowns, and the only equations you can generate are the 2. Again, statically indeterminate. Now, these forces, in all these types of beams, the 2 types of beam we discussed here, we are just talking about external forces, but we are not talking about the deformation of the beam. Now, the other property can cause the deformation of the beam, but we are going to go to that later on. Now, if we talk about you can say the beams may be also identified by types of external loadings, as we have seen here. But what if these concentrated loads were no longer concentrated loads, they were distributed loads? Now this is important. What happens if these loads become distributed in nature? And what will happen to our beam? And you can see a strange load distribution on the figure far right in the presentation. Figure, let me highlight it right here. Now imagine that we have a load distribution with an intensity defined as W. W is the intensity of the load, which can be defined as load. You can say load per unit length of the beam, or the length or unit area it is in contact with. And there are types of intensities, and it is defined as it is a variable intensity, it is a continuous intensity, or it is a discontinuous intensity, and finally with a specific generalized formation. Now if you look at the beam from point A to point C, our loading is variable. It has minimum at one end at point A and is linearly increasing up to point C. After point C, it is creating a constant intensity up till point D, just before point D. And then at point D, it has a significant jump. Now this is a discontinuity right at point D. Now it's not that the forces are changing, because the rate of change of force is so high that it is represented as going straight up. It's shooting up. And from there, from D to point B, it is in a functional wave. You can have a polar parabolic function, or you can say a polynomial is a second order polynomial, third order polynomial, fourth order polynomial wave function can show you the load distribution. Now let us look at what is distributed loads. The distributed loads are shown right here in the 3 types of load distribution. You have the first type of load distribution, which is, you can say, is a uniform area distribution. You can say you have unique formation. The first type of load distribution, if you remember correctly, you have an intensity W distributed over length L. Now the W is defined as load per unit. So sorry about the disturbance. Now let's come back to the topic, distributed loads. Now in the figure, As you can see, there are three different types of distributed loads. First is when your load intensity, that is W, which is defined as force per unit length, that is the dimensions of it, and when you multiply it by length, it will give you the load distribution over that particular length, or you can say give you the magnitude of the reaction force R. Now you have to understand the first case is very simple. W is of equal magnitude throughout the length, it is not changing, and when you multiply it by length, it is going to give you a very simple resultant R. But now the question arises, where is this R located? So what we are going to look at is the shape of this distribution. If you look at this shape, it is in fact a rectangle, and you have studied the centroid, and you know the center of a rectangle defined is simple, half of its length, right in the center, and that is where your R is going to act on a two-dimensional system. Similarly, a second form is when W is uniformly varying, like in case of figure B. It is a triangle and it is spread over a length L, and you are going to get by simple surface area calculations of a triangle, that is half into height into base. You have L and you have W, base and heights, and half times, and you're going to get the surface area of this triangle. Now this area is going to give you the resultant force R. Where it is located, as you have already studied in the centroids of areas, that the 1/3 of the length from the bottom line, from the base, will provide you the L. Now we know that we cannot take the length L, but we can take or assume W to be the base of the triangle, where it is maximum. From there, 1/3 the distance exists. At 1/3 of the distance from W, there exists your reaction R as a resultant, going downwards, acting in the gravitational field. The third case is unique. When two surfaces or more than two surfaces, type of surfaces, load distribution starts acting on your beam. Here we have two different types, a rectangle and a triangle. So what you're going to do is you're going to isolate the two uniform shapes, and for each shape your formulation, your W formulation or weight distribution formulation, is going to define based on the shape their resultant R, the corresponding R's, such as in this case a rectangle is going to generate one reaction, and that is defined by here as R1, and this triangle is going to develop a second reaction that is defined by R2. So you are going to define these R's, and then you're going to calculate their centroids, and from there you can get the load distribution, or you can get the concentrated loads of the two RERs acting on your beam. Now the most generalized form of these are the most generalized form of this R. Now you have two, on a single beam you have two R's, and from there you can calculate the sum of forces acting upward, and it should be equal to an opposite to sum of forces acting downwards, and then the corresponding moments generated by these R's. And if there is another shape, you can also introduce that shape to calculate the load distributions. Now these three types of loadings are very specific in nature. What about the real loadings? The real loadings are slightly different. So let us take one of the most simplest, or you can say the basic form of real loading, and it can be defined in our next slide right here. If you can see, what you have here is a single line or cable that is going in a specific function formation. It could be a polynomial such as a x to power square formation distribution, or simple a linear like x, or you can have to power 3, to power 4, to power 5, different wave formations. You can different shapes can be generated for the cable or load distribution. Now for this load distribution, what you have, how can you find it is, number one, you are going to take one load per unit length, that is one W line. Now in reality you don't have W line. What in reality they will give you, or a specific information will be give you, is load distribution per square inch, for if you're talking in feet, or load, that is the mass of a specific beam per square inch. Cross-section area square inch, which let's say for density point or air force point of steel is, it has you can take a single rod and you cut it in half and look at the cross-section area up front. Now and you take another area and you cut it half, and then you will have a small, very very small cylinder, and that particular volume will have a weight. Now a three-dimensional system, that volume will have weight, and you can say for this dimension of volume, this is the weight of my specific rod. And you can do it by compartmentalizing your entire rod in small volumes which you have originally identified, and that can give you a sense of load distribution over a volume. Now imagine what you do is take a single two-dimensional system like your steel foot ruler, everyone has that, and assuming that foot ruler is single, as you can say, treated as a single cross-sectional area, as a uniform area, what you do is you take each dimension and slice it down, and you weigh the weight of this small sliced area, and you can say the weight distribution of your steel ruler is this much grams per this cross-sectional area, and it is spread over the entire 12 inches. Now that is how you define your weight, a uniform weight. But in this case, simple, a small slice or small weight W, that is load per unit length, acting on this beam right here, acting on this beam. The cross-sectional area, the length it is acting on, is dx. So this is going to generate a very very small reaction. So you can say my dr is in fact W dx. Now this is just one reaction of one load distribution. Now if you want to add all them, you're going to say sum of r from I is equal to 1 to n, there are n r's, you're going to get W summation dx. Oh sorry, you have to understand, W comes into the summation because W is dependent upon this, W dx. Now we know that this sum is going to be equal to the entire R, so we can say this thing as a single R, and we can get that single R should be equal to the summation of all the W's distributed over the small fragment of length x. And this can be written in very generalized form as an integral form from 0 or x1 to x2, and this is what you get right here, a very generalized formulation. Now remind you that W can be a function, and W is a function of x, or can be a function of y, or can be a function of z, depending how your load is being distributed or upon which axis it is being distributed. Now what you have found the R, but for this specific type of shape, where is the centroid? So definition of centroid, since we are moving along x-axis, so centroid can be easily found. It's right here. If you can say there's a bar missing, it's supposed to be x bar is equal to the integral for x W dx over distributed range R. Now you can say what it means is your centroid position is defined as x is the total distribution, how times W, total length of W dx. Now W dx is what? if you remember it correctly, it is in R. This is actually your dr. dr over R. You have found the value of R, detecting right here, found the value of R. So you don't need to change this R. All you need is this dx, because x can be changed, x, because your w is changing with respect to x, and what you are going to get is in fact a uniform position of mass distribution, and you're going to get the resultant, and from there what you're going to get is the position of x. Now this x is the position for each length or distance from origin to the each bar over here, each w acting on this figure right here. It is going to give you the value of x, but not the x bar. X bar is going to be unique for this entire length, which is represented right here. Now this is only for x-axis. If this load distribution is along y-axis, x bar is going to change to y bar. If it is along z-axis, x bar is going to change to z bar, and corresponding your r is going to change from w dz or w dy respectively. Now let us take a look at the two examples. Determine the equivalent concentrated load S and external reactions for the simply supported beam which is subjected to distributed load shown in the figure. Now look at this figure. It's an amazing figure. It is, again, it has divided into two parts. That is, you have a huge rectangle with length over 10 inches, 10 feet, and then you have a small triangle which has a W distribution, a base, and its height can be, you can say, assumed as 6 feet. Now what you are going to do is very, very simple. You have two uniform loads. You're going to get two reactions. That is, the first reaction resultant load is you can say of the resultant load is of the rectangle defined by my diagram, this cross rectangle, and the second R will be from the triangle. Once you have found the R of the two shapes, then you're going to find the centroids. These centroids will be uniquely centered, will be unique. So for a big rectangle, it is right in the center. Since the total length is 10 feet, the center will be half of that, that is 5 feet. The center of the first reaction is at 5 feet. The center of the triangle, as you know from the base, is 1/3. So you're going to get the 1/3 of 6 feet is what? From the base, it is going to be at 2 feet away. So this distance is going to be 2 feet right here. This is going to be 2 feet, and 10 minus 2 is going to give you the 8 feet. Now you have two resultant and you have two reactions. One reaction is at A, the other reaction is at B. So the first equation is sum of moments about A is equal to 0, or sum of forces acting upward should be equal and opposite to sum of forces acting downward. Now you can solve this thing by two techniques. The best way is saying the sum of forces acting upward equal to sum of forces acting downward. This will going to provide you with one equation, and it has two variables, so you will you have the two unknowns are A and B. The second equation is assuming the moment about point A is equal to 0, and you can have the reaction R of the of the rectangle causing the beam to turn about point A in such and such, and the reaction of the triangle trying to rotate the beam, bend the beam about point A in such and such way, and then the counter moment generated by the B should be equal and opposite. This is going to give you two equations, or rather than saying the sum of forces acting along x and y axis, or acting along y axis equal to 0, you can generate a secondary moment equation, which this person has done. and he took the second moment equation saying sum of moment about point B is equal to 0. You're going to get the answer, but the two unknowns in two equations are more than enough. Now, once you solve this thing, I hope you'll get the value of as shown here, RB and RA. You can solve it. This is a very, very simple question. Now let's look at a slightly different question. When your W is a function right here, W naught, this means initial weight is given, load distribution given, plus kx cube. This is how your load is being changing, and he has given the value of k right here. How can you find the value of k? It is given right here. You have got the initial value and the final value. You integrate it along x, you have the value of x. You are going to get a constant. The value of constant is defined as k. Or you can simply put the value and the position of x, and you can find the value of k. Now, here he found out the value of k to be 2 Newton per meter 4. Since I have told you, you can find the value of r is equal to, assuming with our diagrams as he has shown here, this is x-axis, this is corresponding y-axis or wx, and over which you have a function w. So you can say r is equal to integral sign w dx, and you are going to integrate w, which is a function of x, with respect to dx, and you're going to get the value of r right here. Once you have found the value of r, you need to find the centroid, that is x bar. So x bar is x times w, then w will become w naught x plus kx4, and integrate from 0 to 8 meters, and you're going to get the value of x prime, that is 4.49 meters. So you have found the centroid of the load, distributed load. You have the reactions. How many types of reactions you have? You have a cantilever beam, you have two reactions, a moment and a reaction force. So reaction force is sum of forces acting upward should be equal to sum of forces acting downward, and you're going to get the value of AY, which is right here. But the moment has to be the resultant moment force acting somewhere at 4.5. So let's say 4.5 meters, and this is going to create a moment, and then there is going to be a counter moment. So they should be equal and opposite. So m times this is r times this 4.5 should be equal to the counter moment, and you are going to get this answer. Problem solved. So this is how you're going to talk about all the external loadings on a beam. And these, I hope you have understood some vital points about the beam, the external loadings. This is just one part of the beam. In further, we are going to talk about how these loadings affect the beam internally. Now you have to understand, beams are very important for your structural designs. That is all for today. Thank you very much. Assalamu alaikum.